All right, so we are going to kickstart a subject from the 18th lecture that is essentially pretty much a continuation of the ideas that were brought up in the biological membrane videos. And it's really important to understand the biological membrane videos before diving into the membrane potentials. So just make sure you're polished on that before you get started on this subject. First of all, we're going to define what is membrane potential, what causes it, what creates it, and what do we need it for, and how do we achieve it. And also we're going to discuss a brand new idea called the electrochemical equilibrium. We're going to compare it to other types of equilibriums that we know. So let's get started. And first of all, what is a membrane potential? Now let's just say I have a cell and it's floating in an environment. It just so happens that this cell is going to have a slightly more negative charge than its environment. And obviously, when we're saying a slightly more negative charge than its environment, that means that we're comparing this point inside the cell to a point outside the cell. So this is the membrane potential is just a reference. What is the electric difference between the point inside the cell to the point outside the cell? And first of all, why do we have such a thing? Well, it just so happens that all cells need their membrane potential to carry out biological functions. And pretty much every biological function you can think about pretty much needs this. You can think of the membrane potential, the negative membrane potential, as some sort of fuel to run your car. Without it, you can't even turn on the lights, you can't turn on the key, you can't really do much of anything. And when you think about giving an example, the one example as to what process requires such membrane potential, the answer would be action potential. Action potential is one of the biological functions, but it is the one very important one, the one that is always brought as an example. And an example for action potential could be muscle contraction, or signal transduction. Obviously, the latter is for muscle cells, and these are for neurons. And these are the examples that you just have to know. These are the examples you have to know that a lot of times, or oftentimes they ask, why do we need membrane potential? Give an example to different cell types that perform activities or biological functions with a membrane potential. And you need to know muscle contraction and signal transduction. I don't think it's too tough to know. And now we need to think about what is the cause. What causes this slightly more negative charge? Well, it just so happens that the cause for this is uneven distribution of ions across the bilipid layer or the membrane. And what do I mean by that? Let's just say this is the inside of the cell. This is the inside of the cell, and all of this is the outside of the cell. Let's just say I have 3,000 positive ions inside the cell and 4,000 positive ions outside the cell. And this means that compared to the outside, if I compare a point inside and a point outside, compared to the outside, the inside is going to be more negative. And that's what we mean by uneven distribution of ions across the membrane. That causes our negative membrane potential. And what is it created by? It's basically created by the different transport mechanisms. That we learned about. It can be the pumps, it could be the channels, it can be transporters, different mechanisms that take in and put out ions, and they're going to cause some sort of distribution that is going to be slightly more negative inside the cell than outside of the cell. And this is a good time to say that not 100% of the cells are more negative at a potential, but the cells that we are going to work with, or a great majority of the cells, really do have a negative potential inside of them, or Rather, they are more negative than their environment, and they need that to carry out their functions. Some are not, but for our purposes, we're just going to refer to cells having a negative charge as a whole. So cells are slightly more negative than their outer environment, and that is their membrane potential. Perfect. We're going to take the next step and ask, how are we achieving this membrane potential? And by saying constant membrane potential, what I mean is that at any given time, I need to have that negative charge, because if I lose it, I can't really do biological functions. I can't carry out different biological functions that are required for the survival of the cell. So how do I do that? Let's just say I'm just drawing my bilipid layer here. This is my bilipid layer, and I'm going to draw it on this side because I have basically two ways of doing that. Let's just say, and I'm going to take potassium and sodium, and we're going to mention them a lot because they're the main players. They are the main players. Let's just say potassium and sodium. I'm going to take these two. And basically, what I'm saying here is let's just say the intracellular, this is the intracellular inside the cell, and this is the extracellular. This is the extracellular, and this is the intracellular on both examples. So what I know is, let's just say I have, just for example, 3,000 positive ions here and 4,000 positive ions here. Obviously, these are arbitrary numbers. They cannot be really quantitative as an example, but 3,000 ions in, 4,000 ions out, and I really want to keep this number. I don't want it to rise up, because then I'm going to lose my relatively negative potential here. So if I gain one potassium, if I gain, let me switch colors here. If I gain one potassium here, then I'm going to go up to 3001, and I can lose that potassium if I put it back out, if I put one potassium out. Or essentially, if I gain one sodium, I can just export one sodium. And in that sense, for each ion, there is not going to be a net flux. And when I'm saying flux, and you'll hear that often, flux just means the transport of matter over a unit cross-section for unit time, really. And this means that I'm not going to have any net change in my concentration. So instead of saying any net change in my concentration, I'm going to write no net flux of ions in or out. And we know that this is some sort of equilibrium, and this is called thermodynamic equilibrium, equilibrium. A thermodynamic equilibrium, the concentrations don't change because there's no net flux, and also there's no energy required. There's no energy required for this process to take place, because it is in fact an equilibrium. And when I have two systems in equilibrium, no matter or energy is being there is no net transport of matter or energy, because everything is the same and it is in equilibrium. And the thing is that we know this doesn't take place in cells. Cells exchange matter with their environment. They have different environment inside the cell than outside the cell. We have more concentrations of certain species of ions that we have outside, and cells do require energy. So this model doesn't really describe what is going on inside a cell. But still, we need to somehow achieve this membrane potential. Still, I need to make sure that I still have 3,000 positive of 3,000 positive charge inside to relatively 4,000 outside. So I'm just going to write it here. This is my intracellular as well. I'm going to give another example. Let's just say I also have 3,000 positive on one side, and outside I have 4,000 positive, which means I'm good. I have a slightly more negative charge than my extracellular environment, and I want to keep it. How do I keep it? Let's just say for whatever reason, I have one sodium that is coming in. And you can imagine that instead of having one, I can have 1,000 coming in, and this already overthrows my ratio. But let's just say that I have one coming in. That means I'm gaining one positive charge. So how can I balance it? Well, I have potassium, and I'm going to put a little positive here just to make sure that we know this is a positive ion. I have potassium, and just by taking this potassium and tossing it outside of the cell, I'm losing one negative charge. So I'm gaining one and I'm losing one. That way I stay the same. I have my membrane potential stay the same. And when you think about it, this is not a thermodynamic equilibrium, because in order for us to have a thermodynamic equilibrium, we need to have no net flux of energy or matter. And here we have a net flux. So we have a net flux. That means that for a given ion, let's say sodium, there is a difference of flux of transport of particles. So there is a net flux. There's no thermodynamic for equilibrium. There's no thermodynamic equilibrium, and it requires energy. And if you can't really connect the dots as to when would I do this, when would I eject one out, when would I put one in, don't worry yourself yet with the mechanisms, because we're going to get to them. This is just the idea of how do I maintain a slightly more negative charge if I'm taking in sodium, if I need to take in sodium. Here what we said is, hey, I need to take in potassium, but I'm losing my slightly more negative charge, so why don't I take out potassium? But that doesn't really make any sense, because I needed potassium to begin with. So if I took it out, then what am I really getting to here? So obviously this state depicts more what I can expect in a living system. And don't worry, if you don't understand this fully, we're gonna connect all the dots when we get to action potential. So let's keep on going, and we're going to mention a brand new idea that is called electrochemical equilibrium. And both from chemistry and from physics, we know what equilibrium is. Let's just go, what is chemical equilibrium? A chemical equilibrium is a point, let's just say I open the door between two systems and they're at an equilibrium, at a chemical equilibrium. That means that all the concentrations of all the different species within the two systems are the same at any given point, or there is no net flux of particles, of gradients of particles inside the system. The system is at chemical equilibrium, which is good. This is what I want with chemical equilibrium. And what is electric equilibrium? Well, it's basically the same thing, only there's no net transport of charge. But really now I'm going to talk about something brand new, and I'm going to use Professor Varga's great example. And what I'm going to show you is two rooms, room A and room B, and I'm going to arbitrarily change colors like I do. And I have these two rooms, and they're separated by a door that only boys can go through. And I have boys and girls. Only boys can go through this door in any direction they choose. Girls cannot. So this is already a semi-separable membrane, and we know that guys like to be around girls. But nobody really wants to be in a very crowded space. So what can I expect happen? Let's just say this little boy down here says, "Oh man, it's way too crowded here. I'm going over there." So this boy is going to move. We're going to move him over here. Let me erase him from over here. Takes a while. There we go. So this boy effectively moved to the other room because it's way too crowded. It's way too crowded. And maybe one more says, "Oh man, it's too crowded in here. I'm just gonna move back over here, and we're going to delete this little. We're going to move this little guy as well." And now it's not as crowded in this room, but still maybe one guy says, "Oh, there's like 9 people in here. I really want to go out as well." And this guy is going out, and he says, "Oh, this is way nicer. I'm just going to move here," and we're going to move him as well. So being that it's too crowded, these guys want to go to the more spacious room. But now what happens? Now we have 5 guys here and only 2 girls. So this guy says, "Oh man, now there aren't enough girls here, so I'm just going to move to where there are more girls." Perfect. And we're going to delete it from here. And what we really want to have happen, or what really is essentially going to happen, is that now we had one person or one guy move to this side because there aren't enough girls, and now this guy is going to move here because again it's too crowded, and instead of doing all this game, I'm just going to move this guy over here. And basically all of this motion, the take-home message is that at a certain point in this whole idea, I'm going to have a state in which for every guy moving to the right side room because it's too crowded, I'm going to have a guy moving to the left side room because there aren't enough girls. And that means there would be no net transport of boys. Why? Because for every one moving because, oh, it's too crowded, there's one going back because there aren't enough girls. And how does that relate to electrochemical equilibrium? Well, let's bring the chemistry into it, and I promise it's going to be very simple, very easy chemistry. Very, very, very simple and easy, I promise. Now we have two rooms that are separated by a semi-permeable membrane. And this membrane has very small holes in it. And potassium is a smaller ion than chlorine. So potassium can go in and out if it chooses. It can go in and out. And we can distinctively see, without even looking at the numbers, we can see that we have a lot of potassium here, a lot of potassium in this room, and less potassium in this room. And the same for chlorine. That means that we would have a chemical gradient driving both of these guys through. What we need to remember is that only potassium can go through. Chlorine cannot. So what do you imagine would happen? I'm just going to take some potassiums and move them because they really want to be where they're going from a high concentration to low concentration. And this is a very, very strong force propelling them. A chemical gradient force. And I'm going to take these bunch of potassiums and move them here. And let's consider what happens now. Obviously, these numbers don't no longer represent the situation because a bunch of potassium moved here. What happened here? Slowly, more and more potassium moved to this side, and this side gained potassium, and this side lost potassium. So this side, let's say side A lost potassium. So it means it lost positive charge. And this side B, gained positive charge. So this side is going to be slightly more and more positive, and this side is going to be more and more negative. And consider that this side had more negative ions to begin with. So it's going to very dramatically become more and more negative. And we know that potassium ions are attracted to negative charges. Let me just arbitrarily turn colors. This is going to be very negative, and this is going to be very positive. No, I don't like this color. There we go. This is going to be very positive. And we know that potassiums, they love the negative charge. So the negative attraction, the ionic electric attraction, is going to attract these ions to go back. And at a certain point, I'm going to have for each potassium ion going inside because it is very ionically attracted. I'm going to have one potassium going here because there is a chemical gradient or because there are less potassiums here. Obviously, you can imagine a lot more potassiums here. It's going to be a lot more. So again, we have somewhat of an equilibrium because we have for each potassium going to the left, I have one potassium going to the right. So let's consider the forces. A potassium would go from the left side to the right side because there's a chemical gradient. That means it wants to go, whenever you hear chemical gradient, oh man, what a T. Whenever you mean chemical gradient is just say wants to go to low concentration. That's a chemical gradient. So this chemical gradient is driving this transition here. And what transition would get sodium to want to go to the left? Well, it's the ionic transition or the electrical transition. So we have an electric, you can say gradient, but I would say potential. or driving force. You can also say gradient. It's not incorrect. I just like to use different terms for different forces applicable, so I wouldn't mix them around. And now, being that we have an equilibrium, because at some point, just like the boys and girls, there's no net transport of potassium, or boys. And when there's no net transport, we have an equilibrium, and these two forces are at equilibrium. Thus, we have an electrochemical equilibrium. An electrochemical equilibrium. And in this sense, you can see that in the example, we have a slightly more negative environment here, and this should clue you in to what side is the cellular side. This side is the cellular side, and I'm going to relate it a little bit later, and this is all going to add up and make a little bit more sense. All you really need to know now is there is a possibility to equilibrate these two forces due to the chemical gradient and the electric difference. Perfect. See you in the next video.